So as promised, we are now looking at martingales under Brownian motion on the stochastic processes playlist. Okay, so if this is a new concept for you, it's welcome you here. Definition of a martingale. It is basically a stochastic process. A stochastic process, which is a collection of xn for n greater than or equal to 0, is called a martingale with respect to a filtration Fn. We looked at the concept of a filtration in the last video when we looked at the properties of a Brownian motion. So there's a filtration Fn if the expectation of xn plus 1 given Fn, which is the filtration, is equal to xn. Now, so the interpretation here is that the expected future value equals the current value. All right. The expected future value is equal to the current value. So no advantage can be gained using past information. That's basically what Martingale is about. And of course, you will see why this is used for a fair game because you don't have nobody has an unfair advantage in if you're tossing a coin or rolling a die or something. Nobody has a prior information that is going to confer on them some undue advantage. So talking about the intuition of martingale in a fair game, if you consider a fair coin toss where getting a head is +1, getting tail is -1. So let xn be total winnings after n steps. Then we say that the expected value of xn plus 1 is given fn is equal to xn. So this simply represents a fair game because no information you've had previously is going to help you. No advantage can be gained using past information, basically. So we have a simple example here talking about random walk. So don't forget that a Brownian motion is simply the limit of a random walk. So when you take several steps in a random walk, you hit a Brownian motion. So let xn be the summation from I equals 1 to n of yi, where yi is +1 with probability 0.5. That's like getting ahead or whatever else. When in a coin toss with probability 0.5 and getting -1 with probability 0.5, or more like having a son, with probability 0.5 and having a daughter with probability 0.5 also, something like that. So then we say that the expected value of yi is 0. That's +1 -1. That simply gives 0. So if you need to prove the reason why the expected value of a Brownian motion is equal to 0, so this is one way to look at it. So you have +1 -1. So it's like you hit a wall and then the wall pushes you back somewhere. So that's the kind of thing. So expected value of yi is 0. So expected value of xn plus 1 given fn is simply xn. Thus, we say that xn is a martingale. It's a martingale like that. So, we have some key properties of a martingale. First of all, we have constant expectation, which is also true for Brownian motion, like we already know. So, constant expectation, meaning the expectation of xn is equal to expectation of x naught, right? Then martingale difference. If you let d sub n plus 1 be equal to xn plus 1 minus xn, then the expected value of d n plus 1, d sub n plus 1 given f sub n will be equal to 0. So because normally the expected value of xn plus 1 given fn is always xn. So xn minus xn will simply end up giving you 0, right? So and then there's no predictable gain, and that's why it is good to measure to model fair games. So no predictable gain, like we said already. Past information cannot be used to gain advantage. And then we have sub-martingales and super-martingales. So for a martingale, of course, we know already that the expected value of xn plus 1 given fn is equal to xn, right? So for sub-martingale, it means that the expected value of xn plus 1 given fn is greater than or equal to xn, right? So the current step is greater than or equal to xn. So this is a sub-martingale. But then you also have a super martingale where the expected value of xn plus 1 given fn is less than or equal to xn. So super martingale, the expected value of the current state is less than the previous state. Sub, the expected value now is greater, than the previous state, like that. But martingale, the expected value at this state is equal to the one at the previous state. So those are talking about sub martingales and super martingales, and of course the martingale itself. So talking about stopping time now, a stopping time T is a random time such that the decision to stop depends only on past information. Example, so you stop when xn is equal to 10. So that means stop after 10 steps or stop when bankrupt. So or stop when maybe if you're maybe Ludo, playing Ludo for instance, I don't know Ludo, I don't think Ludo is that global, right? But it's a game that is very popular in Nigeria. So once all the so you have four seats, you have four squares and each two players, four players can play. Let's say four players are playing, right? So each player has a square. So once they succeed in getting out all the seeds in their square, they are done. So that's it. We already have a criteria there for stopping time or stop when bankrupt. I don't know. Maybe this is applicable to Monopoly. That once you go bankrupt, you are done. Something like that. I'm not too sure how if that is true. Then you have optional stopping theorem. If the stochastic process, or if you like the Brownian motion, which is a martingale, right? Then T is a stopping time with technical conditions like, so if we have Xn to be a martingale and T as a stopping time with technical conditions, then we can say that the expected value of X sub T is equal to the expected value of X sub 0. And the meaning here is that you cannot beat a fair game by choosing when to stop. Yeah, you cannot beat a fair game by choosing when to stop. So, um, that is what we have there. So for we can then have Python simulation for random walk. Don't forget Brownian motion. Martingale is a Brownian motion, and we know Brownian motion is actually random walk at its limit. Okay, random walk after several steps. So here now we are simulating various. We are taking 1,000 steps for various possibilities like this. So you just have all of that, you know. And as you keep running, it keeps changing. Oh, okay. I think this one is fixed. Is it fixed? I think it is. Yeah, I think it remains the same over time. So this is random walk, which is a martingale now. So as the steps are going and time is passing, that's the behavior you have right there. Okay, and the reason why it is fixed is because we have set the seed here. So if I comment this out now, the shape should keep changing each time you run it. Okay, should keep changing. So you see it's changing now because I've removed the seed. So and that's also a good lesson that if you are working with randomness and you don't want, because it's good, especially in research, we always want to have the same results, you know. So because you want to have the same results, you have to set that seed. So np.random.seed, and you set it at whatever, maybe 0.42 or whatever, to make sure that you have reproducibility of your results. And then we have optional stopping simulation. Okay, so let's say you have you start an optional stopping simulation like that. So you import numpy as, so this is taking so much time because we have 10,000 trials. Okay, so and here we have the result, simulate game for in range n trials, and then we print average outcome, which is minus 0.164. So this is 0.164. If you run it again, it takes some time. Let's see what the answer comes out to look like. So we are setting the value to be between like okay, minus one and one. No, I don't think. Yeah, but yeah, the answer is like minus one, between minus one and one. So the average outcome is going to be constrained between minus one and one like that. So and then we have advanced martingale example. So let Sn be a random walk and define Xn to be Sn squared minus n. Then we say that the expected value of xn plus 1 given fn is equal to xn. Thus, xn is a martingale. Okay? So if this holds, we know we are dealing with a martingale for sure. Don't forget, fn is the filter in that situation. So in this case now, if we follow this now, we take 100,000 steps. That's a lot. So, and we take for the steps now, we now say n period random choice between minus 1 and 1, size of n steps. Then we now say s is n period cumulative sum of steps now, you know, and then we now have x defined as s squared minus the range of from 1 to n steps plus 1, like that. That's for all the 10,000 steps. And if we keep running, it keeps shifting in value like that. Okay, then we can then talk about martingales in finance. A price process ST A price process ST under a risk neutral measure satisfies the expected value of S sub t plus 1 given f of t, given ft rather equals S sub t. Applications, you can have applications of this in option pricing and arbitrage theory. Then we have common misconceptions for martingale betting system. Doubling bets after losses does not guarantee profit, right? So this requires infinite money and limited by table constraints. Then you have the fact that martingale is not equal to increasing. Martingale does not necessarily increase. So a martingale is not necessarily increasing because it is fair, right? So in summary, we have that a martingale is a fair stochastic process. Future expectation equals present value. No predictable profit strategy exists. And then it is widely used in probability theory, finance, and stochastic calculus. We're going to stick stochastic calculus probably after this Brownian motion set of videos. I think that we're looking at Ito calculus and all of that. So we have some practice problems here. Let yi be independent, would be independent and I keep forgetting what this IID is. It is independent. It is independent and why do I keep forgetting this IID? Independent IID. Uh, Independent and identically distributed. Yeah. So let's yi be IID, independent and identically distributed with expected value of yi being equal to 0. So show that xn is summation from I equals 1 to n of yi is a martingale. Okay. So prove that for any martingale xn, expected value of xn is equal to expected value of x naught. Now that is necessarily true because a martingale is a Brownian uh, motion. So let yi be Bernoulli and define this. Show that xn is a martingale. You know, then you simply just want to show that the expected value of xn and x naught is equal to 0, basically. Then let xn be a martingale. Show that this, of course, we know that the expected value of xn plus 1 will be xn. So that just gives us, so if we subtract, we just have 0 right there. So yeah, we basically did this in the just not quite long. So look at this and see how well you can try your hands on them, and let's see if you get it. So if you have any issues with any of the questions, feel very free to let me know in the comment section, either on YouTube or on Facebook. Again, let me show the questions. So here we have questions 1 to 4. So questions 1 to 4 here. Then 5 to 10. So 5 to 10. Then we have 11 to 15, 11 to 16, say 11 to 16, and then 7 to the end, and the rest, right? So try your hands on them and let's see how well you get the gist. Let me know how helpful this is for you. And there's something else, if there's something else you'd like me to do to try, feel free to let me know. If you have subscribed to this channel already, I appreciate you for that. If you have not, why not go ahead and hit the subscribe button and of course hit the notification bell afterwards so you can always get alerted each time a new video is released. You can also become a member of the channel by clicking on join. That gives you special privileges like seeing the videos exclusively or being the first to see some videos. We can also hang out to discuss whatever interests you on the channel. You can request for PDF copies of my notes. All right. So ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.